Today is a smart grid project in Europe. I will try to summarize what I did in some European projects. And at the beginning, I will start to give you some examples, and after that, we can go to see what happened in the some of my European projects. Let me just introduce briefly about my background. As you mentioned, I finished my PhD project at UPC, Catalonia Institute, University of Technology in Catalonia, under full PhD scholarship from Catalonia Institute for Energy Research. This is very high prestige research center in Barcelona, and when I started my PhD project, this is was only the second research center that microgrid has been was developed in Europe. And immediately after graduation, I started my postdoc research project at the University of Manchester. I started with a corporate project, which was one of the biggest European project in Europe. And after that, after 2 years, I started my second postdoc researcher with University of Manchester. And the project was Novel Grid project, and this is also is a European project. After 3.5 years, I moved to University College Cork in Cork in Ireland. So I work as a researcher in both Marine Research Center and UCC University in Ireland, and this was a common project between US and Ireland. And after that, after a few months, I moved to Northumbria University uh, as a lecturer, and after 1 year, I promoted to senior lecturer, and right now I'm an associate professor at Northumbria University. So this slide shows very briefly about my research interest, and the grant has been awarded by myself and in collaboration with other people. My research interest is optimal and control strategy in distributed generation, optimal scheduling of the demand side management, generation side management in the smart grid, mathematical modeling, and integration systems, multi-energy carrier, and so on. Some of my selected funded research, you can see in this in the left-hand side, around in 2000. Last year, I got a grant from EPSRC, and a part of this grant has been supported by one company in Newcastle, and this grant is using to support the PhD project, and also 2 years in 2019. Yeah, I got a grant from British Council. This is a common project between our university and two universities in India, NIT Rourkela and IIT Goa. Sorry, and I got two RDF grant, and at this moment, my future leadership fellowship has been revised 2 times, and I'm still waiting to receive a feedback from the UKRI, and also one of the research project funded by QNRF in Qatar also has been accepted. This grant is around $6,000, and another one which is around $6,040 is under review, and we passed the second stage. Hopefully, we will get a feedback these days. But because of coronavirus, we have a delay around 2 months. And also, I got two grants from Qatar University to support the PhD project, and one grant from King Abdulaziz University uh, uh, under a scholarship from the KA Care, the Ministry of the Atomic and Renewable Energy in Saudi Arabia, because I am also honorary distinguished adjunct professor in King Abdulaziz University because of my citation. This is my Google Scholar. As you can see, my H index is 33 and my H10 index is 67. Okay, my presentation has been divided into several parts. First of all, I will start to give you a very short explanation about some of concept, and after that, we will see some simulation and result and discussion, and finally, we will talk about the project that I already involved. So, uh, as you know, multi-energy carrier systems is introducing by is supported by several energy carriers such as electricity networks, hydrogen, gas network, heat network, cooling systems, and so on. So, in order to create an interconnection between these networks, we need to use different technologies such as a fuel cell, CHP, combined heat and power, and combined cooling heat and power system, electrical heat pump, gas boiler, and so on. So the question is that how we can operate this system optimally, and how we can increase the reliability of the systems when we have an unwanted event. I forgot to mention that here around a few days ago, another my research proposal has been accepted by EPSRC. This is only 7 months and is around 70,000 pounds, and this is about integration of the electrical vehicle in the multi-energy carrier systems. The question is that how we can have a smart transportation systems, and how these smart transportation systems can support other type of the yes, networks such as the electricity, hydrogen. For example, if you have a storm in the city and a part of our electricity networks has been damaged, how a smart transportation systems can support us to meet at least a part of our load demand. Because electrical vehicle, as you know, is can be considered as a mobile energy storage. So in the near future, we will have a huge capacity of electrical vehicle, and this can create a good potential for us to support our load demand, or to reduce the unmet power, or to mitigate the interruptions in the power supplies. So in summary, I can say that today's system need to be re-infrastructure, and uh, future the customers in the future and power producers can meet each other under some a few intelligent and smart solutions, and also new technologies such as renewable based technologies are coming. As you know, this kind of technology most of times they will reduce the inertia in the network because they don't have a rotational. Most of them they don't have a rotational um, part, and as a result, the inertia of the systems can be increased, and we have to propose some solution to increase the inertia of the systems in order to keep the our voltage stability and frequency stability in the systems. And also by using of the renewable based technology, we can improve the quality of the environment, and we can reduce the CO2 emissions, and we can have more clean environment. So if I wanted to summarize the benefit of the integration systems, as you can see, carbon emission reductions, we can reduce the CO2 emission, we can reduce the unmet power or unserved energy systems, and also, however, we have some uncertainty in this kind of technology, but by using of the uncertainty modeling, we can reduce the uncertainty condition of the uncertainty parameters. So, for example, if we are going to schedule the systems, whole systems, including the electric vehicles and integration systems, and PV, photovoltaic, wind power generation, and so on, because of changing weather condition, we cannot predict how much power can be generated by photovoltaic and energy storage. And in addition, electric vehicle is moving from one point to another point, so predicting the exact location of the electric vehicle is so difficult. So in order to solve this kind of problems, we have to know how the uncertainty can be modeled, and there are some methodology to solve this problem. I will explain later in my presentation, for example, Taochi methods, and I will let you know briefly how this method is working. And also, we can maximize the utilization of renewable-based technology. We can reduce the capital cost due to the conventional power plant, because if we can distribute generations and the most power, necessary power can be generated by renewable-based technologies, so we can reduce the possibility of the building big power plants. So instead of big power plant, we can have distributed generation systems, and so central controller in this case also is more complicated and can be more the complexity will be increased. So if we have distribution systems, and if we can have a distributed control systems, in order in addition to have a less complexity for control, we will increase the reliability of the system at the end. And also we can increase the flexibility of the electrical power systems. So it means not only we will have the um, um, we will have the some generation unit that can generate electricity. We will have some generation that can generate both electricity and thermal, so they can support other type of our networks. And in addition, for example, for by using of macro CHP, we can consume the gas network, and we can generate both electricity and thermal. So, and electrical heat pump, as you know, can consume the electricity, and it can generate the thermal power. So we can support different energy carriers here. So flexibility will be increased. If we lost one of the our electricity network, the other networks can support us to supply our load demand. And also we will have some opportunities for business. It means in addition to have electricity networks, we will have the gas electricity retailers, we will have the gas retailers, thermal retailers in the future. Even we will have some retailers or aggregators to support our smart transportation systems. And finally, we can reduce the congestion and so on. So as you can see here, previously we will have the we had conventional buildings. As you can see, they are just consuming the power from the upstream grid. And in a few years ago, the retailers and different distribution system operators are introduced to the electricity network, so they can make a competition with each other to sell the power to the conventional building. And but nowadays conventional buildings is converting to the green buildings. So we will have renewable based technology inside the green buildings. And these renewable based technologies can support supply our electricity buildings. So as you can see in this figure, the owner of green buildings can be one of the players in this framework, because this owner will try to invest some renewable based technology, for example, photovoltaic systems or energy storage or micro CHP. And they can install this technology inside the building, and tenant or customers will be considered as another most important player in this framework. So as you can see, the passive distribution network will be converted to the active distribution network. It means customers not only can play as buyers, they can also participate to sell the power to the to the other players. For example, here we will have a lot of green buildings in the neighborhood systems. It means the tenant, by participating in the responsive load demand programming, they can manage the the load demand, and after that the extra power can be sold to the other building in the neighbor, or it can be sold to the upstream grid. So we will have the distributed controller here, and locally we can implement a local one um, independent uh, controller for each of these green buildings, and finally the information from each buildings can be shared with a central controller in the top, and this central controller based on the objective function, for example, maximizing the social welfare in the whole systems, can make a decision how much power can be uh, can be shared from one green buildings in the neighborhood systems to other green buildings. It means if one of them has extra power, so what we can do, what is the best way to use this extra power, and this extra power can be sold to the one green buildings with a shortage power in the neighbor, or another green buildings again with a shortage power. How much power should be shared, and what is the offer prices to sell this amount of power. So for this kind of framework, we need to implement a bidding strategy to find out how how much what is the offer price to for selling or buying the electricity. And in addition, at each time interval, some of the green buildings can make it can create a coalition with each other, and they can make a decision at which time interval they can create a coalition with each other, and also sometimes they make this maybe they can say that collaborating in the coalition formation cannot give them any benefits, so it's better to work independently, so they can split out from the coalition formation. So here the question is that if they can create a coalition, how much power they have to generate, and how much power is better to be shared with other buildings, and also this is good to keep continue the coalition, or it's better to just split out from the coalition formation and work independently. For this kind of framework, I implemented a similar intelligent framework by using of the game theory approach. So I already implemented the Nikaido Aizodo relaxation algorithm to have different type of the players. So I implemented cooperative and non-cooperative game for this kind of networks. Oh, sorry. Yeah. So as I mentioned, in this framework, we will have a lot of players. So we are trying to implement the market operator based on the transactive energy. So here, sharing the power, keeping the security of the security and privacy of the players are all are considering the transactive energy. So transactive energy and other concepts, for example, peer-to-peer energy, supply chain, a lot of concepts we will have in this framework. So if we want to have implement market operator based on transactive energy, in this framework, we will have a lot of players. For example, retailers. These retailers can be either electricity retailer or gas retailer, thermal retailer, as I mentioned in the multi-energy carrier systems or integration systems. We will have different type of the retailers. We will have distribution system operator. We will have the owner of home microgrids. We will have the customers or tenant. So each of these players are trying to follow their own objective function. For instance, from the customer's point of view, they are interested to minimize the electricity price. So if this complicated framework can reduce the electricity price for them, they will be happy. Otherwise, or maybe we can give them some incentive factor to participate in this kind of framework. And also the owner of the green buildings. The owner of green buildings are trying to maximize the market clearing price, because in this way they can their investment cost or capital cost will be returned to them faster. So they are thinking that if they can invest some money to install the renewable based technology, for example PV systems or battery energy storage, how long it takes time to pay back their investment. So if the market clearing price or electricity price can be maximized as much as possible, they will be happy. And also from the distribution system operators, they are interesting to keep the voltage stability voltage stability in the systems, in the LV systems, low voltage systems, distribution level. So why? Because as I mentioned, renewable based technology, increasing the number of renewable based technology will reduce the inertia in the network. So in order to distributed system operators are not happy to and lower inertia is equal to, it means we will have the instability in the system. So the distributed system operator will not be happy. There are a lot of methods to increase the stability of the system. So we have to use them. And also from the transmission system operator point of view, as you know, mismatch power between the generation and the consumption will create unbalanced power in the systems, and as a result, we will have the frequency and stability in the system. So from TSO operators, growing up the number of the renewable resources should be based on the having the frequency stability in the systems. Otherwise, maybe it can be so critical for them. So we have a lot of players here, and each of players are trying to looking for their own objective functions. And later I will show you. So this objective function, how we have to create uh, how we can compromise between this sometimes opposite objective function, and we how we can make happier all of the these players at the same time. So as I mentioned, green buildings can, we will have green buildings in the near future, and these green buildings can be operated independently in the autonomous mode. It means they can be isolated from the upstream grid, and or it can be connected to the upstream grid, and it can operate as a grid connected uh, mode. But these green buildings also can be connected in neighborhood systems. It means we can have a lot of green buildings in the network, and they can share the power between each other, and also they can sell some power to the conventional buildings. So if we want to implement a very simple optimization algorithm for this kind of networks, I just put the include a flowchart, very simple flowchart to have energy management systems in this kind of systems. So this flowchart, as I mentioned, we will have the central controller in the top. We can call this central controller neighborhood system operator, and we will have some local control for this one. So for each of these buildings. On the other hand, we can have a bi-level optimization algorithm, and that in the top level we will have the central controller, and in the lower level we will have the buildings or customers in this level. We can implement multi-level optimization algorithm, but this one is only single level optimization algorithm. This algorithm has been developed in the higher levels for neighborhood system operators. So as I mentioned, we will have the weather condition is uncertain parameters. So we have to apply uncertainty modeling for solar radiation and load demand and so on. If you have a electric vehicle in the building, so arrival time, departure time, initial value of the SOC, and EV preference, and a lot of uncertainty can be considered as an uncertainty modeling. And so after uncertain, and also market clearing price also is a uncertain parameters. So it means as you know, the market clearing these parameters can be changed based on a lot of inputs. So it should be considered as a uncertainty parameters. And after uncertainty modeling, we have to send the output of the uncertainty unit to market operator based on transactive energy. And here in this unit, we can have a different type of the optimization algorithm, such as the heuristic optimization algorithm and the realistic optimization algorithm. So for example, a heuristic optimization algorithm, partial sum optimization, or harmonic search, or dynamic Ewing or Bass methods, and so on. So we can use this heuristic algorithm, or we can use a realistic method and we can use different solvers such as the Cplex, Conop, depending on the nature of the problems. For example, the problem can be linear or nonlinear, or if we have mixed integer linear programming or mixed integer nonlinear programming, we will have the different methods and different solvers. And also I included one very interesting uh, very interesting website. Here you can you can have most of the optimization algorithm, and also, for example, if you want to see how each of these algorithms is working, you will have a lot of um, video to show that how because all of this heuristic algorithm is based on the nature behavior of the animals. So you can see how this algorithm working, and you will have the code also here. And also this person will explain that how the code can has been developed and how we can um, uh, implement this kind of the methods. In this website also you will have a lot of examples. So if I wanted to summarize them, one of the heuristic algorithm, for example, partial sum optimization algorithm, as you can see, this method is a population-based optimization method inspired by social behavior of the bird, and they are trying to move from one point to another point, another location, and um, uh, so we have to have two first assumption. They know how far the food is in each iteration, and also what is the best strategy to find the food. So to follow the bird which is nearest to the food, each single solution will be a bird in the search space, and each of these point should be considered as a particle. And also we will have we need to define the fitness values and velocities. And for PSO we will have we have to have we have to calculate the location of the particle and also velocity. And after each iteration, we have to consider the best solutions, and finally we will find the global optimal results. This is a velocity of each particle. As you can see, the locations and the coefficient factor can be changed, and based on this coefficient factor we can change the location of the particles. But for example, these weighting factors cannot be so high, because maybe we can pass the optimal global optimal solutions. So this is a flowchart for PSO. After each iteration, we have to check that this is if we define the objective function as a minimization of the operating cost. After in each iteration, we have to check that what is the minimum this new result is a minimum value, or the previous one is should be considered as a minimum value. So this is one of the small project in Manchester. We had several green buildings. As you can see, there are several um, uh, technologies, different type of technologies. For example, um, uh, energy storage, electrical boiler, thermal energy storage, electrical heat pump, solar thermal panel, gas boiler, and CHP. And also for each of buildings, we have to I model all of appliances, for example, dishwashing, refrigerator, and heat water. So for this project, for each of the green buildings, we implemented a local controller, and we will have a central controller um, f- um, for whole systems. So we will have this topology in the green building level. We will have three players: producers, customers, and prosumers. And in the neighborhood system level, we will have maybe we can have different neighborhood system operators and central neighborhood system operator level, and we will have a grid level. We will have the retailers here, this DSO, and so on. So this is a approach can be implemented for this kind of uh, networks. So by using of the first of all, as I mentioned, we have to apply the uncertainty, and after that, uncertainty has been modeled by Taguchi method, and after that, the optimization algorithm has been implemented. So we will follow up the four stages. First of all, heuristic data, such as the wind speed, solar radiation, load demand, and after that, we can generate a scenario, and we can implement the scenario generation by using of different methods. For example, um, uh, 2-point estimation, 4-point estimation, Taguchi method, IGGT, a lot of methods we have, and after that we will have the optimization algorithm. So in order to find the heuristic data, we can use the renewables.ninja website. So here, for example, I use the Barcelona, our Catalonia analysis for energy research as a for the load demand, and after that, um, this is a forecasted data for solar radiation and wind speed and load demand. So how we can actually implement the uncertainty modeling. As you can see, this is a normal distribution networks, and for example, at 10 a.m. our PV is generated. We will have a 3.3 kilowatt power for PV, so this one can be considered as a mean value, and we can generate a lot of scenarios between the 0 and this mean value. So a standard, for example, this is at 10 a.m. and our PV is here. So, and after that, so inside this distribution curve, um, if our mean value is 3.3 and a standard deviation is around 0.9, so we will generate a lot of scenarios in this inside these curves. And we have three uncertainty parameter here. So in the Taguchi methods, we have a table is based on the table, and Taguchi is inherently is a scenario reduction. It means we don't need to generate so much scenarios. So if we have three columns, three uncertainty parameters, we can use, for example, a table with 4 columns, and the last columns can be equal to 0. So, and we have to define the level for each of the parameters. For example, if we have in level 2 and the minimum and maximum value for PV is around 0.8 kilowatt and 5.2 kilowatt. So in level 4, we will have 2.2, and we will have two values like equal to 1.9 and 4.9. So we will have these two values. We can do something similar for the rest of the uncertainty parameters. And regarding the probability, each scenario should have one probability. For example, if the power of PV is 1.9, so the probability can be equal to 1.9 is equal will be in this area, so the probability will be equal to this value. So we generated scenarios and we generated all of probability, so we can do something similar for the rest of the uncertainty parameters, and at the end we can calculate the objective function. So then the objective function should be sorted based on descending sort values, because we are going to minimize the operating costs. So this one can be considered as a minimum value. So this is some of our results. As you can see, this is a consumption curve, and this is a production curve. And in order to check the valuability of the result, both of the generation and consumption should match to each other. And this is a total consumption power for each building and total generation power for each building. So as you can see, for electrical and thermal network, if we implement the optimization or algorithm for each green buildings, we will have the different profit and cost, operating cost. As you can see, without the optimization algorithm, our profit is more or less than the when we are using the optimization algorithm. So this figure showing us the how much the total amount of electrical power generated in green buildings for in each green buildings, for example, based on the different methods. So, and also this figure slide showing us the total amount of electrical power produced from the retailers. And here you can see that how much power can be generated by each of the our generation unit in each buildings. For example, this one is based on the partial optimization algorithm. As you can see, for example, 1 p.m. At here, for example, this is a gas boiler. So at 6 p.m. The around 69% of the power has been generated by gas boiler, and for example, and around 69 around 69 power also has been generated by CHP. So if we and also I develop the model by using a realistic optimization algorithm. So as I mentioned, we have two operating mode: single grid connected home microgrid and multiple green buildings in the neighborhood systems. So as you can see in this slide, we have a demand response programming. As you know, we can shift a part of our load demand from one time interval to another time interval based on the electricity price, or if we are in the on-peak period. If we are in the on-peak period, um, so on-peak period, so it's better to shift our unnecessary load demand to another time interval that where we are in the off-peak period, and also electricity is cheaper. And sometimes maybe you can ask me if we move this amount of our load demand to the other time interval with a lower electricity price, it means that the electricity price will be increased. So we have to find a solution to limit the amount of our load shifting. So this is a operation of the energy storage and market clearing price. As you can see, market clearing price has been reduced. This is a prediction data. The market clearing price has been reduced in most of the time intervals. In the grid connected operating mode, you can see that this is a load demand. Also, load demand for each building has been changed. The profile has been changed based on the demand response programming model. And also you can see that energy storage for each buildings has more values, so it can, on the other hand, we can increase the reliability of the systems. And here you can see that, for example, after 24 hours, 24 hours, we will have the SOC around 80%. It means we can keep these values for another day to supply our load demand if we have any unwanted event. For example, we lost our upstream grid. This energy storage can support us. So as I mentioned, we will have a lot of green buildings, a lot of players in these systems. So from the owner of a home microgrids are trying to maximize the profit. The customers are minimizing the market clearing price. The profit can be maximized if the market clearing price will be maximized. So between these two players, we have to create a trade-off between them. So, and also from the retailers that are trying to maximize the profit, from the distributed network operators that are trying to increase the voltage stability, and from the national grid or the transmission system operator that are trying to reduce the consumption. So after this introduction, I'm starting to explain about the project that I already involved. Corporate project was my first project in University of Manchester. In this project, I tried to formulate the coalition formation strategy combined with responsive load demand programming based on the transactive energy framework in the neighborhood systems. And then I try to solve the optimization problem for maximizing the total profit of the multiple home microgrid systems, and considering the uncertainties. And also I try to understand how profit can be allocated between the home microgrids fairly, and how we can have more stable coalition formation between the players. And this one was my first case study. As you can see, this case study is a very a research center in close to Paris. We had 3 green buildings, including several type of the technology. And green building C was 100 number of the student dormitory union, and but I integrated in only one green buildings in order to simplify the case study. And also this is our input data. As you can see, we have input data, so regarding the our loads and so on. And this is a part of a result. As you can see, if each of the green buildings are working independently, they will get a less revenue in comparison if we have a coalition formation between them. This is a dual coalition formation, and this is a grand coalition formation, or a triple coalition formation. So this is a market clearing price. As you can see, if each of green buildings are working independently, the market clearing price is lower than the predicted data. And if we have a dual coalition formation between the 2 green buildings, we will have the less value for market clearing price. And in the second Naval Grid project, I tried to find how we can have a different type of the demand response programming. So in the demand response programming, in addition to include the offer-based demand response programming, I also modeled voltage stability in the demand response. On the other hand, we want to see, for example, this is one of case study in south of Greece, and we had a lot of green buildings, and each of green buildings, I assume that each of green buildings are interesting to participate in the demand response with a price, or demand response with emission, and also demand response based on the stability. So if we have this model for demand response, what will be happen in the what we can do for scheduling. So this is some of result. As you can see in this slide, in this figure, this building is participating in demand response based on the emissions. So algorithm mentioned that this amount of load demand is better to shift it to other type of time interval. This green building is operating as a price based, and so on. So this is one another case study for Naval Grid project. This is a 300 buses systems in UK. So I developed a similar idea for modeling of the demand response in the buildings in the distribution network level. We had 11 transformers, and for each green buildings, I modeled all appliances. Some appliances are controllable, model based on the controllable impedance. Some appliances are model based on the impedance, constant current, constant power, and for example, refrigerators can be modeled as an induction motor, and so on. So same as other algorithm, we need to get some input data: load, demand composition, CO2 emission curve, electrical price curve, and this input data will send to the optimization tools. The optimization algorithm has been implemented in GAM software, which is a software very useful for to implement the optimization algorithm. And the objective function was defining based on the minimization of CO2 emission, minimization of peak shaving, minimization of operating costs, and voltage stability system index. And after that, the output of the optimization problem will send to the Dix-Allen Power Factory to study the stability. And then in the Dix-Allen, I will run the simulation, and I will have optimal power flow, and then we have to check the voltage stability index. If the voltage stability index is in the alloy range, we will go to the next time interval. Otherwise, this process should be repeated again. Then after in the Credence project, which was a common project between the US island, I tried to focus on the creating the coalition formation between the more players, and in addition to have a different model of the demand response. I wanted to know how demand response programming and energy storage planning can be integrated to each other, and how they can improve the the possibility of the coalition formation in the system. So this is an algorithm that has been implemented based on the game theory approach. As you can see, the data will send to the step one. In step one, we will generate some scenarios, and then after that, unit commitment will be implemented for each home microgrid, and after that, price-based unit commitment will be developed for scheduling of the retailers in each scenarios, and most of these inputs will send to the step 4, which is the calculating the expected value and applying the Nikaido isolated relaxation algorithm method. And finally, we will find the market clearing price and the profit of the players. So this is the input data, including the power produced by photovoltaic, wind turbine, and non-responsive load or critical load demand, and this is the market clearing price. So different case studies has been implemented. So finally, you can see the market clearing price is changing based on the and is lower than the market clearing price, predicted market clearing price. And recently, as I mentioned, around 2 years ago, I started another project under the British Council grant in collaboration with 2 Indian universities. So this grant is coming from the UKRA, and it is almost finished. Most of the part has been finished. We are trying to just summarizing and preparing our report. So this project has been divided into 4 sections. And first of all, we started to develop a smart charge controller for electric vehicle in the domestic building. We implemented experimentally a microgrid in the lab, and different method has been developed based on the fuzzy controller, and later I will explain that how it's working. And also we implemented multi-agent control systems for both DC microgrids and AC microgrids. So this one also has been finished. We published 3 papers, and after that also we implemented solar PV forecasting based on the different methods. And finally, this is the final step, and Also, simulation has been finished, and we are in the writing of the paper process. So we want to implement the power and energy management in the microgrid systems. So a smart charge controller. For a smart charge controller for electric vehicles in the domestic microgrid, or even it can be applied for a shopping mall, because uh, the purpose smart controller can be applied in different application, but not for charging station. For charging station, we have a very short period, and so we need to use other control strategy to satisfy our players. So for this smart charge controller, we use the fuzzy logic controller. This is our microgrid in the lab. This microgrid has been including the photovoltaic systems installed in the roof, battery energy storage, battery management systems, and active load, bidirectional chargings, and one of the active load is operating as a to model the electric vehicle. So this is so what we are trying to do. We are trying to implement a smart charge controller that meet the EV user requirements, support the grid, charge EV from the renewable energy, and minimum degradation cost for electric vehicles, and energy storage battery. So this is all of our objective function. So this is a block diagram of a smart charge controller. As you can see, we have a battery management system, we have a user input, we have a smart meter to measure the grid. So we will from the energy storage, we need to battery management system, we need to calculate the we have to know about the initial value of a state of charge, and we can find our energy storage at each time interval. But this smart charge controller should be able to calculate and estimate the state of charge of battery in the electric vehicle based on the arrival time, departure time, duration period for charging, mileage of the users, and target C rate, and so on. So yes, yeah. So we want to. So what is the C rate? It means, for example, if we have a good photovoltaic system, so it's better to use the extra power for the to charge our battery. So C rate can be higher. If the electricity price is low, so also it's better to charge to increase the C rate of the battery. And also if for example, if the electricity price is very high, so it's better to just is electricity price is very high and we don't have enough photovoltaic system, so it's better to reduce the C rate for energy storage. So this is a schematic diagram of the smart charge controller. As you can see, this is a battery management system user requirement. This is a target miles, plug-in time, plug-out time, and based on all of these inputs, the uh, this controller will be worked. So, and here, as I mentioned, we have to define several membership function based on the different scenarios that can be happen. For example, if we have high power produced by PV, what we can do, and if electrical vehicle is available, it's better uh, uh, to use this power to charge our energy storage. But most of the time, electrical vehicle is available after 6 p.m. So at that time, we don't have electrical photovoltaic power. So this one can be used to charge our energy storage. And so if we have only three inputs, such as EV user travel requirements, lengths of the next journey, travel and weather condition, or battery state of health and grid condition, for example, voltage. So we need to define the 55 rules in total for fuzzy logic controller. But if we have four inputs, for example, this three input plus the PV output, so we need to define the 163 rules. If we have five input, it means all of these the above four inputs plus the electricity tariff, we have to define 487. For instance, if we want to increase the number of inputs, we will have we need to define more rules. As a result, we have to find a solution to increase the ability of the fuzzy logic control for this control for our application. So here uh, we use the neural network to just train our whole systems, and then the if we want to add a new input, this new input will be insert to the our neural networks. So here, if tariff is very high, so C rate should be reduced. If tariff is low, C rate should be increased. If voltage is high, it means we need to use the electrical vehicle in order to reduce the voltage. So C rate should be high. If our PV output is very high, C rate should be also very high. So we will have some result here. So as I mentioned, by increasing the number of the inputs, our fuzzy controller will be increased. We need to define a new membership function. So it's better to use the neural networks methodology in order to create a train for neural networks. And after that, we can use this neural networks. So this is our output. We define three objective function. First objective function is related to maximizing the C rate while fulfilling the constraint. Objective function, the second objective function is maximizing profit while fulfilling constraint, and third objective function is maximizing C rate and profit, both of them at the same time. So we will see the result, how the C rate is changing, and what we can do. This is a part of results, so it has not been published yet. We are writing this paper at this moment. and but one paper has been revised in IEEE transaction on industrial application at this moment. The second task is multi-agent control. Here, we defined the several agents. So, for example, PV agent, grid agent, active load agent, and so on. So this one has been simulated in the Simulink. As you can see in this slide, we will have the different agent. So also this one has been developed, has been published in the two papers. The objective of this multi-agent system is that how we can implement real-time algorithm to control the all agents and how they can be self-healing, and if you have if one of the agents can will have some problem, how other agents can help to solve this problem. This is a solar PV forecasting, and this is solar forecasting. So for solar forecasting, we implement several methods, satellite method, sorry, uh, physical method, statistical method. We implemented ARMA, and we tested all of these methods and compared each other. And we our paper also has been revised in renewable energy for this section. So so this is what we have done for British Council project. Regarding the other projects with Qatar universities and Texas A&M University in US, I didn't include any result here because we are still working on it. Yeah. Thank you so much for your attention, and please, I would be so happy to answer any questions if you have.
Thank you, Dr. Mousa, for that overall picture of the various projects that has run in collaboration. So now it's time for a discussion. So if any of the participants would like to add or would like to discuss anything related to what discussed so far, so you can unmute yourself and you can feel free to talk with Dr. Mousa.
Yes.
Yeah, so I think there are no much questions. So one question that I would like to ask is, what is the
Yes.
stage of smart grid implementation in UK? Or yeah, so is it still in the phase where we are doing research, and or is it in a stage where in some places it is already we can say that that is a smart grid? So is there
Yeah.
any anything, what is the stage there?
Yeah, actually, this is very good questions. Sorry. This year, government funding some projects related to the green hydrogen, and how green hydrogen can be utilized significantly in the electricity network. So I'm just trying to submit a proposal in this area to see that how we can have the hydrogen-based electrical cars to support the hydrogen networks, and also how hydrogen network can support the electricity network and vice versa, how the electricity network also can support the hydrogen network. And also as I mentioned, a smart developing the smart transportation system is a most important things, and this area is still is very hot topic, and we are there are a lot of idea are coming for this in this area. For example, how electrical vehicle can improve reliability of the systems, how resiliency of the systems, how they can help us to to minimize the peak shaving or smoothing our load demand in the load in the demand side management and so on. So there are some topics, hot topic in there in this area that based on the government policy, because next 10 days all of cars in UK should be replaced with the electrical vehicles. So this is very important to prepare all of infrastructures, propose a lot of intelligent algorithm, and recently in collaboration with Sheffield University, I'm submitting another proposal regarding the electrical vehicle, how electrical vehicle can participate in the urban planning and so on. So this is a good potential in this area at this moment.
Okay, okay. Thank you, Dr. Mousa.
Yeah,
So,
fine.
any other questions from any participants? Okay, fine. So we have recorded the session. So I will share the recordings with you so that you can go through it later as well. And
Yes,
if you would like to talk with Mousa, you can always mail him. So his mail ID is
yes,
available in his personal website. So
yes,
we are encouraged to contact him as well. So
yes,
on behalf of the department as well as on behalf of the participants, I would like to express my sincere thanks to Dr. Mousa for spending
yes,
time with us and sharing the details of different projects that has related to smart grids. So,
yes,
so thank you very much. With this, we'll stop this session and we'll move to the next session tomorrow. So,
yes.
thank you very much, Dr. Mousa, for joining.
Thank you
Thank
so much. Thank
you.
you so much for inviting me and all of audience to take a time for my presentation. Thank you so much. Have a very good day.
Thank you. Thank you.
Thank you. Bye bye.
So fine. The feedback link is provided in the chat box, so you can fill that and you can give the feedback of the session. And the next session we'll have tomorrow at 9 a.m. and that will be on smart grid projects in India. It will be taken by Sunita Chauhan from Power Grid Corporation of India Limited. Okay, so the link will be same for the session tomorrow. You can join in the same link tomorrow at 9:30. So please note the change. So the timing for tomorrow's morning session is 9:30 in the morning. Thank you very much.